Okay, so this is section 4.1 in your textbook. I think most of what we did for 1.1 to 1.3 was in chapter 3. But I would have to go back and check to see for sure. But when you guys open up your numbers files, it'll tell you what section it is in the textbook, so that if you want extra practice, then you can, like I said, do the odds, check the answers in the back of the book. That way you can get an idea of, or get more of an idea, more of an understanding. Okay. All right, so we are going to talk about functions, which I'm confident is something you guys talked about in Algebra 1 and Algebra 2 as well too, but we need to review all the ground rules of what makes a function a function. We first start by talking about something called a relation, because there's a bit of a difference between the two, but in math, anytime you have usually we think about it like two variables, any sort of correspondence between the two is called a relation. So functions are subsets of relations, but they have a little bit more specific properties, okay? So a relation is any way that we can relate two sets of data together, okay? So like y and x is the most common relation that we talk about, okay? So if x and y are elements in these sets and a relation exists between the two, then we say x corresponds to y, or y depends upon x, and we write it as x and then an arrow and a y. So we would say we could say x corresponds to y, x goes to y. So y depends upon x implies that y is your dependent variable, making x your independent variable. And I know that's all things that you guys have heard of before, okay? So there's many examples of relations that we can have, and there's a lot of different ways that we can write them. We can write them like a set of ordered pairs. So we've got the curly brace here, which indicates that we're talking about a set of something. And then inside we have a couple different coordinate pairs. So 3, 5, 2, -4, -4, 1, and 5, 0. This would be a set of values that represents a relation, okay? You could have like a mapping relation. So it shows, this is another way to express that same information. So we have -4 goes with 1, or -3 goes, or 3 goes to -4, 2 goes to 5, 5 goes to 0, as it does in the set of coordinate pairs up here as well too, okay? We could express that information using a table. So x are independent variables here, mapping to one dependent variable y. So that's another option that we have. And then we also could put it on a graph. So we can label all these coordinate points on a graph, but each one of these are examples of relations, okay? All right, now, these are two words that I know you're familiar with, domain and range. When we think of domain, what do we think of? What variable are we working with? Yeah, so then range is going to be our y values. So x is your set of independent variables, okay? And then your range is going to be the set of all of your y values, okay? So a function is any relation that associates each element in x with exactly one element in y. So that exactly one is the key part of that definition there, okay? So each x value gets mapped to exactly one y value. You can't have an x value that goes to more than one y value, okay? There's a test that you guys learned at some point that would violate. Does anybody remember what that test is called? If you have an x that goes to two different y's? Vertical line test. Yep, Colin is right. Amog was going to say the same thing, and a lot of you were thinking the same thing, I'm sure. Your vertical line test, okay? So it's got to go to exactly one element, otherwise it doesn't work, okay? So we've got a bunch of examples here. An example of something that would represent a function, like a set of coordinate points that would be a function, 2, 5, 3, -1, 5, 9, and 8, 9. What we need to make sure is that each independent variable goes to exactly one y value. Now, we could have two different x values go to the same y value. What we can't have is the same x value go to two different y values. That would be an issue. So for example, we've got 5 going to 9 and we have 8 going to 9. That's okay. We can achieve the same output twice. We just can't have the same input go to two different outputs, okay? You can think about like a practical application of that would be temperature. Like if we're talking about like temperature and time of day, like, this morning, it was like, God, it cold this morning, right? It was like 50 some degrees. Will it get to 50 some degrees again today? It could, like maybe in the evening, right? The temperature is like the highest point now, but it's going to dip again. I could get down to 55 degrees again. So we've got 2 different times of the day going to the same temperature. That's fine. We can have that. But like if I'm talking about one specific location in this classroom, could it be like 40 degrees and then also 82 degrees at the same time? Like in one specific part? No, that wouldn't represent a function. So that doesn't work. Okay. And then how that looks. So for example, non-function examples would be like 3, 5, 3, -1. We have the same x value going to 2 different y values. So a repeated x going to 2 different y's, that's no good. And then what that looks like on a graph or on like a mapping relation, we've got p, q, and r. Those are inputs into our function. And then we have each one of them is going to one specific y value and exactly one y value. So p goes to m, q goes to n, and r goes to n. That's fine. We have 2 different inputs that are going to the same y value. What we can't have is one input going to 2 different y values. We can't have that. So that would not represent a function. Okay. And then if we have a graph, has to pass vertical line test like you guys mentioned already. This one is good. This one is no bueno. Does not work. Okay. All right, cool. All right, so notation y equals f of x can be used. You guys have used that many times before. Y is your dependent variable, x is your independent variable. How that notation works, if you have a table, n, your independent variable, we've got some values listed there. Q would be your output. Here, f of n is equal to your output q. So then if we want to use that notation, f of 2 would be an output of what? Yep. All notation you guys have seen before, but just a little bit of a review. What would I plug in for x or my input n to get an output of 7? Yeah, so 3 is what our input would be. So that's how that works, okay? And then below, if we have h of p equals p squared plus 2p, let's find the following, okay? So h of 4, what is that asking me to do if it wants us to do h of 4? Yeah, plug 4 in, right? So we would get 4 squared plus 2 times 4, which gives us what? 4 squared is 16 plus 8 gives us what? Yay, 24. All right, now the other one is h of p equals 3. How does that differ from the one we just did? Yeah, so we got to put the p, like we got to keep that there. But what are we going to do with the 3? Yeah, we replace h of p, or we set it equal to 3, right? Oh, you were doing the a plus h, weren't you? No worries, we'll get there in a second. So 3 equals p squared plus 2p. Let's solve that, okay? How would I solve that? If I wanted to figure out what p would be, what would I do? Good, Gideon. So 0 equals p squared plus 2p minus 3. What is our factorization of that? Plus 3 minus 1, how's that sound? Cool. So then we end up with p-values of -3 and +1. A skill you guys had to use a lot last night with factoring and finding zeros. All right, Isabel was gung-ho to do the next one. What are you telling us to do, Isabel? What should we do?
Just keep a plus 8 the same and just square both of them like a square plus h squared equals 2.
So you're telling me this is my input and I need to plug it into these 2 placeholders, right? Yep. So what this looks like, let me change my color since I kind of bled in with the other one here. What that looks like is I would end up with, because I have p squared plus 2p, h is going to replace the p. So I would have quantity a plus h squared plus 2 times a plus h. And then what Isabel's advocating for us to do is go ahead and square that out and combine like terms. We got to be careful though. When you square 2 terms added together, I can't square each one individually. What should I do with that? Do we remember how to handle this situation right here? It doesn't end up being a squared plus h squared. Don't worry, I had a calculus kid do the same thing today, so don't feel bad. Anybody remember what happens there? How I handle that?
Make it like two separate factors.
Yeah, I got to write it twice and multiply them by each other. So what I need to do is I need to make this a plus h times a plus h. Because that's what it means to square it. We got to multiply it by itself. Plus 2 times a plus h. And then we need to distribute those two things to each other. Okay, I'll show you that it doesn't end up being the same thing. So a times a is a squared. A times h is plus ah. And then I have another set of AH plus AH. And then H and H is H squared. And then if I distribute the second set, 2A plus 2H. And then I combine like terms. A squared plus... I have two AHs there. So I'm going to write it as plus 2AH. And then plus H squared. And then plus 2A plus 2H. Okay? All right, so it does equal a squared plus h squared, but then there's that plus 2ah in the middle as well too. It sneaks on in there. Okay, all right, questions there? That's about as simplified as I can get. There's not much more I can do. Okay, all right. So again, what you're plugging in, a plus h, just replaces the placeholder of p that was in your problem. Okay, all right. And then, yeah, okay, cool. Now, we can also find domain and range from a graph as well too, which is usually the easier way to go about doing it, okay? So we'll write it in inequality notation and in interval notation, so we're well versed with both. Now, again, you guys already told me, when I find my domain, I'm looking at my x values. When I look at my range, I'm checking out my y values, okay? All right, so let's look at x values first in my graph up above. What would be my interval of x values that I'm working with? What's my leftmost x value? -5, yeah, so it goes as far as -5. That's my point here, corresponds to this x value there. How far right does my domain go? Yeah, it will keep going. Even though my graph is going down, it's still going to the right, okay? So then I'm going to go from -5 to infinity. So if I write it in inequality notation, how would I write that for my domain? X is going to be between which two values? -5 and positive infinity. So I could do -5 is less than or equal to x, which is less than or equal to infinity. Although, would I put less than or equal to if I'm working with infinity? No, because I can never actually equal infinity. So let's go ahead and erase that equal to sign. Okay. All right, let's do our range. How far down does my graph go? -infinity, right. How far up does it go? 5, okay. So then we would do -infinity is less than y. Now, do I have equality at 5?
Yeah.
I do. So less than or equal to 5. Okay. Let's write them in interval notation, which is usually how I prefer to write it. So for interval notation, we could say x is an element of, and then what will that interval look like? Good. Yep. -5 to infinity, bracket around the -5, and then parenthesis around the infinity. Very good. Okay, cool. And then let's do the same thing with range. So y is an element of what? Good. You said what? -infinity to 5?
Yeah, and a bracket.
Nice. Okay, cool. Hey, take a second and do the same thing for the one down below. Lulu, do you prefer to write with your finger, or is your stylus dead?
It's dead.
Stylus is dead. Okay. One adjustment I've had to make since coming to Revere is keeping all of my things charged. There are so many things that I have to keep charged. The MacBook and the iPad and the stylus. All right. Inequality notation, domain. What do we got? Who's feeling brave? I'm not just going to rely on Gideon and Amog the whole time. I want to hear from the rest of us as well, too. Lulu, go.
-3 is less than x, which is less than or equal to 1.
Do you guys agree with Lulu? I agree with Lulu. That looks good. All right, what about range? Inequality notation, range. What do you think? My y values. Isabel. Less than or equal to y, you said, which is what? Less than 0. Let's have a conversation about this one. This one's tricky. So definitely takes a value at -4, right? And then we see this open circle here at this value right here. But is there anywhere else on the graph that it takes a y value of 0? Yeah, this one's weird. And I would say technically that it does take a y value of 0 right up here. So because of that, I'm going to put an additional line, inequality sign, right under there. Does that make sense? Okay, cool. All right, let's write them in interval notation. Domain. What would my interval notation for domain look like? Get in.
Instead of -3, and then 1, the bracket again.
So x is an element of -3. You said to what? 1 with a bracket on the end? I like it. What would be my range? Y is an element of what? Isabel?
Bracket, -4, 0 bracket.
Perfect. Okay, questions there? Feeling all right? Yay. Cool. All right. We've talked about zeros a little bit already. I mean, I kind of name dropped that vocabulary word in the last section we were looking at, okay? But what's referred to as the zeros of a function are the values that make the function equal to 0. On a graph, we refer to them as the x-intercepts. So it'll definitely be a core component of this course is analyzing the zeros as we get into different types of functions and how to solve them and what that deals with on the graph. Okay. So we've got a couple functions here. We've got 3 over x minus 4, and we want to find the domain, the zeros, and the range. And then we also have a quadratic or a square root function as well too. Okay. All right. Let's talk about domain first. Okay, so one thing I didn't formalize, but I know you guys have seen in the past, is domain. We can have some issues with domain. We can't plug any x into any sort of function that we have. What type of rules can we not break in math? What can we not do when it comes in terms of domain or just evaluating things in general? What's like the golden rule? What can you not do in math? Can't divide by 0. So when we're finding our domain, we need to find the value. We need to find which values we're going to exclude, and that would be anything that would make the denominator equal to 0. What else can we not do? If we want to get a real answer, what can we not do? Yeah, and how do we get imaginary numbers?
Square root of a negative.
Square root of a negative, right? So we can't take square root of a negative number, and then we can't have a 0 in the denominator, okay? All right, so looking at the first one here, we've got a denominator, okay? So polynomials, those domains are all real numbers, okay? You can plug anything into a polynomial. This is what's referred to as a rational function. It's a polynomial divided by another polynomial, okay? So anytime we have division, we have to be extra careful when it comes to domain, okay? Now, this one's pretty simple to see, but what x value is going to give me an issue when it comes in terms of domain? 4, right? Because that's clearly what makes a denominator equal to 0. If I wasn't sure, I would take that denominator, x minus 4, and then I would set it equal to 0. and find if any values make that denominator 0. And in case it does, we would get x equal to 4. We would say it's a 0 of the denominator, okay? Now, are there any other numbers that are going to give me an issue aside from 4? Nah, that's it. It's the only one. So how would I write that? I'm going to do it in interval notation. How would I write that I want every number aside from 4? How could I write that in interval notation? X is an element of what? I want every number but 4. 4 is the only one I don't want. Andy?
Negative infinity to 4, parentheses, and then 4 to infinity.
Perfect. So negative infinity to 4, and then I'm going to union it with 4 to infinity. Very good. Okay. All right. Let's talk about range. Well, actually, before we talk about range, we need to talk about zeros. Okay? So the zeros are our x-intercept, and it's any value that makes the function equal to 0. So if I want to find the zeros, does anybody remember what that process looks like? What I need to do if I want to find the zeros of a function? It's the same process if you want to find the x-intercepts of a function. Yeah, so when we want to find intercepts, you're right. We're going to replace either x or y with 0. In this case, since I want to find the x-intercepts, I need to replace y with 0, because that's where it crosses the x-axis is when y equals to 0, okay? If I want to find the y-intercepts, then I would plug in 0 for x, okay? So Isabel's right. What I'm going to do is I'm going to take this function and I'm going to set it equal to 0, so 3 over x minus 4, okay? Now, if we want to find the x-intercepts, or if we want to find something that makes our function equal to 0, hello Siri, we're not really concerned about the denominator. Because if the denominator equals 0, that's a whole different situation, right? Because then my function is undefined at that point. So when you have a fractional function, or a rational function in this case, and you want to find the zeros, you really need to set the numerator equal to 0. But when I do that in this case, what happens? Can I set 3 equal to 0? Is that going to give me anything? 3 doesn't equal 0, first off. And second of all, there's no variable to solve for. So does this graph have any zeros? No. So there are none in this graph. Okay? And I'll show you what the graph looks like here in a minute. All right, so now that brings us to range. So that means my graph never crosses the x-axis. Okay? But it's defined everywhere else aside from 4 for my function. So if you look at the function itself, can I plug numbers in to make that function positive?
Yeah.
I can, right? I can plug in a number and it'll give me a positive output. Can I plug in a number and it'll give me a negative output as well too? Yeah, so I have values above the x-axis, below the x-axis. How high can I go? I mean, can I go all the way up to infinity? Let's talk about what happens if we plug in some of these numbers. So let's say I plug in I don't know, 10. If I plug in 10, what happens to my function? I get 3 over 10 minus 4, which would give me 3 over 6, which is what? A half. What happens if I plug in 20? Because what I'm doing is I'm finding what happens as I go to the right. Okay, if I plug in 20, I would get 3 over 20 minus 4. So 20 minus 4 is 16. So I get 3 over 16, which is some sort of decimal, right? Bigger or smaller than a half? Smaller. So what's happening to my outputs as x gets really big? It gets closer to 0. And Colin, that's a great way to put it. The bigger my x values get, my outputs are just going to get closer and closer to 0. Okay? What happens if we go the other direction? Let's say I plug in I don't know, 1. What would be, or let's say I plug in, I don't know, 5. Let's say 5, for example. So I'd get 3 over 5 minus 4. 5 minus 4 is going to give me what? 1, right? So 3 over 1 gives me an output of 3. Well, that's certainly bigger than a half. You'll find out the closer I get to what number, the higher my outputs get. Because what happens if I pick because I can't do 4, right? What happens if I pick 3? If I pick 3, I would get 3 minus 1, which is negative 1. 3 over negative 1 is negative 3. Then I flip to the negative side of things, okay? But what if I wanted my values to keep going up? I'd have to plug in numbers that are closer and closer to what value? 4. Let's say I plug in 4.1, okay? So if I do that, and that may be even worth writing, so 3 over 4.1 minus 4. And this is kind of me like nerding out a little bit. I'm just bringing you along for the ride. So 4.1 minus 4 gives you what?
0.1.
0.1. What is that as a fraction?
1/10.
Okay, so then that would be 3 over 1/10. It's a weird way to write that. How can we like clean that up so it's not a fraction within a fraction? What would I have to multiply by?
10.
Okay, so if I multiply top and bottom by 10, what do I get?
30.
30 over 1, which is just 30. So now my outputs are getting bigger, okay? Does anybody have any idea what this graph looks like? If I graph it, it looks something like this. At 4, we said we have an issue, right? Does anybody know what takes place at 4? Since I can't plug in a number, does anybody know what exists on my graph at 4? An asymptote. Have you guys heard that word before? Vertical, horizontal asymptotes. You guys studied that in Algebra 2? Okay. I beg I ask your forgiveness for my ignorance because I don't since I'm still new, I'm still learning like the scope and sequence of every course and like where you learn things. So I'm just trying to like gauge that from you guys. There is a vertical asymptote here at 4, which means as my graph gets close to it, we already saw it's like hugging 0, but as it gets close to it, it's shooting up to infinity. What happens on the other side? We already saw we can have negative values, right? So it's symmetric, but it's reflected over that asymptote, okay? So it's going to look something like this. For what it's worth, you have another asymptote on the graph. Do you know what asymptote that would be? 0, yeah. So you're going to have a horizontal asymptote of y equals 0. There's going to be an asymptote there as well, too. So then what's my range? How far down can my graph go? Negative infinity, right? How far up can it go?
To 0.
Positive infinity, but Andy's right. I can't have an output of 0. There's an asymptote there, and we talked about that. There's no zeros of the function. So I have to break up my range into 2 different values, and I should put y as an element of. But negative infinity to 0, and then unioned with 0 to infinity. Okay. Questions there? Sorry, I just like went full nerd there for a second. I just get so excited about functional analysis. It's one of my favorite things. I'm sorry. All right, domain. Ooh, we got square roots now in this case. We got to be careful. All right, so we got to talk about the type of numbers that we can plug in here. Now, what type of numbers do we want under a square root?
Positive.
Yeah, we definitely want it to be positive. So how could we rewrite this so that we can find out where what is under the square root gives me a positive number? Really what this does is it goes back to your homework from yesterday.
It's like making an inequality.
Yeah, we're going to do 1 minus t squared needs to be greater than 0. Now here's a question. Can we have a 0 under the square root? What's the square root of 0?
0.
Yeah, and that's defined, right? So I'm going to make it 1 minus t squared is greater than or equal to 0. And then this just turns into a problem like your homework yesterday, right? How do I factor 1 minus t squared? What does that look like? Can I factor it? Yeah, I can factor it. What's it look like?
1.
Good, Collins. It's going to be 1 minus t, 1 plus t. And then you guys just play the same game that you played last night. So we need to test intervals from negative infinity to negative 1, from negative 1 to 1, and then from 1 to 0. Or, I'm sorry, from 1 to infinity. So let's do that real quick. So negative infinity to negative 1, negative 1 to 1, and then 1 to infinity. All right, negative infinity to negative 1. What number do you want to plug in? Could be anything. Could be negative 2, could be negative a million. What do you want to check? All right, negative a million. So if I plug in negative a million, 1 minus negative a million, will that be positive or negative?
Positive.
Positive, right? 1 minus negative a million would be positive. All right, what about 1 plus negative a million? It'd be negative, right? So I have positive times a negative. So what sign is that giving me? Positive or negative?
Negative.
Negative. Okay. So do I want that interval? No, I don't. Okay. What about from -1 to 1? What do you guys want to test?
0.
Probably 0, right? I'm not even going to fight you on that one. Okay, 1 minus 0 is positive. What about 1 plus 0?
Positive.
Positive. So overall, what sign am I getting?
Positive.
Nice. Hey, we want that interval, right? Because we want 1 minus t squared to be greater than or equal to 0, so we want that one. All right, what about from 1 to infinity? Do you want to test 2 or do you want to test 1,000,000?
2.
Very good, let's test 1,000,000. So if we do 1 minus 1,000,000, positive or negative?
Negative.
Negative. And then 1 plus 1,000,000?
Positive.
Very much positive. So a negative times a positive is going to give me a negative. I don't want that interval. So then my domain is going to be, ooh, what variable do I use here? T, very good. That's my independent variable. T is an element of -1 to 1. Okay. Now, can it equal 1? I kind of messed up when I wrote my intervals. Can it equal 1 and can it equal -1? Yeah, because what do you get under the square root if it equals 1?
0.
Yeah, so I should not put parentheses here. I actually should put a bracket. All right. What about zeros? I want to find my zeros. What do I need to do to find zeros again? Set it equal to 0. So 0 equals square root of 1 minus t squared. Okay, how do I solve that? What should I do to both sides?
Square.
Mm-hmm. So then 0 equals 1 minus t squared. Then what do I want to do? How do I solve for t? What do you guys want to do next? We can factor it. Okay. So 0 equals 1 minus t. We already have that factorization in our back pocket, so we might as well use it, which gives us two t values, 1 and -1. So those are going to be my zeros. Okay, so I have a t value of 1 and a t value of -1. Okay, I didn't finish. That's okay. Because we've done some zeros before as well too. Okay. All right, so your homework, I'll just post it to Google Classroom. I'll just put it as a announcement on Google Classroom. It's in the book. Yeah, no worksheet tonight. It is in the book. Okay. Now, spend some time reviewing 1-1 to 1-3 because you have a quiz on it on Tuesday. Okay.